would like to thank the organizers for the opportunity to give this talk. My name is Michael Tribelsky, and I am from Lomonosov Moscow State University. This is a logo of my university. And I will tell you something about nanoparticles as a tool to tailor electromagnetic field at subwavelength scales. Actually, there are plenty results obtained in this field, and I have just 20 minutes for my talk. So it's impossible, even briefly, to describe the whole subject. I will give you just a very brief sketch. And if somebody is interested in detail, please don't hesitate to drop me a message. This is my email account, and definitely I will reply you. So this is my university and outline of my talk. I have to tell that I am not a material scientist. I am a physicist, so do not expect to learn from my talk about new materials. I will tell you about physical grounds for new materials, and to create new materials based on these grounds is actually your task, not mine. So I will give you a brief introduction. Then, as I said, I will describe the physical grounds of the phenomena discussed. Then we will discuss light scattering by small particles. We'll begin with the very well-known Rayleigh scattering. Then we will discuss anomalous scattering. This is an absolutely new effect, absolutely new phenomenon. Then we will move to higher index dielectric particles and peculiarities of light scattering by these particles. Specifically, we will discuss tunable scattering diagrams and giant field concentration, so-called funnel effect. Then we will discuss dynamic effects, which are very important for short pulses, conclusions, main publications, and funding. So light scattering by a sphere. It is a very old problem, and the exact solution to this problem was obtained many years ago by several prominent scientists. There are some most well-known of them. And it seems that the question is closed. Fortunately, this is not the case, because a formal mathematical solution is very cumbersome. And nowadays we have new parameters and new tools to operate with light. And in this range of parameters and with the help of these new tools, we can open completely new opportunities, absolutely unknown to these prominent scientists at that time. And these opportunities actually is a topic of my talk. So then, as I said, physics lies in the new range of parameters and new scattering peculiarities related to these parameters. Why is it important? Because nowadays we have a tremendous progress of different nanotechnologies. And the main question is how to, on the other hand, we have a very powerful energy source, such as numerous types of lasers, which operates with light. And the question is how to overcome the diffraction limit, how to make the action of a laser beam as small as possible. And the second related question is how to tailor and control the radiation pattern at a subwavelength scale, the scale which is much smaller than the wavelengths of the incident radiation. These questions, maybe 50 years ago, could sound absolutely nonsense, but nowadays we can see that it is possible. So there are two reasons for that. First of all, this is academic reasons because it's interesting, a very interesting topic. And as I said, there is huge demand from industry, from numerous applications, medicine, biology, data processing, telecommunication, and so on. And of course, these two cases are interconnected, and they are enhanced each other. The academic results stimulates new technologies, and demand from the industry stimulates new academic study. So then I remind you light scattering, Rayleigh theory of light scattering. This is the very well-known topic. You could find a description in any textbooks of optics. So the efficiency of the scattering is described by the cross-section, which is actually the ratio of the power scattering in the all directions to the power density of the incident light. So the dimension of this quantity is square centimeters, and it is given by the following expression, where epsilon is the permittivity of the scattering object. Because of this, x is what is called size parameter, and actually this is the dimensionless radius of the sphere divided by the wavelength of the incident radiation. We are talking about this range where x is a small parameter. Because of this x to fourth power, we can enjoy the color of blue sky and scarlet sunset. So this formula is was tested experimentally numerous times, and no doubt that it is correct. But let us look at the denominator of this expression. We could see these two terms, and epsilon is the function of the frequency, and there is no restriction to the sign of this quantity. So it should be positive and it could be negative. And if epsilon equals -2, we have 0 in the denominator, and we have infinitely large cross-section for a small particle, which is nonsense, of course. How to save the day? First, we can remember we should remember that epsilon is a complex quantity. So any real material has certain dissipation rate, and the dissipation is described by the imaginary part of epsilon. But suppose now that the imaginary part is very small. Then this quantity 2 could cancel the real part, -2, but cannot cancel the imaginary part. So then we have the imaginary part in the denominator. But if the imaginary part is very small, then a particle with the size of a few nanometers can have the cross-section of about a square kilometer, which is nonsense again. So what's wrong? The wrong point is that this simple formula does not take into account that a particle is a resonator, and it has its own eigenmodes. And when the frequency of the drive coincides with the frequency of the eigenmode, we have a resonance, and we have a huge amplitude of this resonance if the dissipation is small. That is actually what we have. And these eigenmodes in the range of negative epsilon are called surface plasmons. They are very well known. But what is the surface plasmon? It's oscillation of free electron gas, and electrons are charged particles, and if they oscillate, they radiate electromagnetic wave. And this wave takes out energy from the particle. So it means that even the particle does not have any dissipation, we still have energy losses related to this radiation. So it is also a well-known effect, and it's called radiative damping. And to describe it, we should add to the dissipative part, we have also dissipation, damping, not dissipation, related to non-dissipative processes, which is called a radiative contribution. Usually, this is a small quantity, and it could be neglected. But if epsilon is small, epsilon double prime is small, then just this quantity becomes dominant. And then we face a new effect related to this radiative damping, and we will focus on it. This scattering of light, which is bounded by the radiative damping, qualitatively different from the Rayleigh one, just because epsilon double prime is a constant, and this quantity depends on the parameters of the problem. So then in different range of the parameters of the size and frequency, we have different radiative pattern. To get the qualitative expression quantitative expression for the radiative damping, we have to look at the exact solution and to replace the Rayleigh approximation by the exact mean solution. If we do that, we could see the radiative pattern, which has very little, actually nothing in common, with what you could find in any textbook. This is the field of Poynting vector. This is the streamline of this Poynting vector. We describe the flow of energy in the vicinity of a small spherical particle with Z permittivity. And there are some sketches, there are some cases presented here with different values of permittivity approaching the resonance value. And you could see rather a complicated pattern. And what is important is, this is the center of localized plasmons, which I told about. This is the final effect. So you could see this separatrix, and it acts as a funnel. It collects the radiation from the broad inlet and transforms it to the very small outlet in the close vicinity of the particle. As a result, we have a huge concentration of the electromagnetic radiation in a very small volume, which is much smaller, whose size is much smaller than the wavelengths. Okay, so moreover, we could see optical vortices and all other peculiarities, and all the scales, I stress it again, all the scales here are much smaller than the wavelengths. So in 3D, it looks even more complicated. The wavelengths, for the comparison, you could see this is the wavelengths, and this is the streamlines of the Poynting vector. You could see a very complicated structure, which depends on the frequency and the size of the particle. And changing these two parameters, we can control this field distribution at the subwavelength scale, which is very important, as I said, for numerous technologies. Okay. What about dielectric particles? Why metal particles do not exhibit the pronounced resonances usually? Because, as I said, the necessary condition for the manifestations of these effects is related to low dissipation. Unfortunately, almost all metals at optical frequencies have a large dissipative rate. Exceptions are aluminum, potassium, and sodium, but they're chemically active and not very convenient for applications. So the idea is to replace metals with dielectric. So for dielectrics, permittivity is positive and plasmonic modes are suppressed. They cannot exist. But instead, we have the electromagnetic radiation, the incident wave, induces polarization of the particle, and instead of plasmonic modes, we have polaritonic modes associated with the polarization of the with oscillation of the polarization of the particle. So, and instead of the instead of oscillation of the free electrons, we have oscillation of the bound electrons, oscillation of polarization, and we have displacement currents instead of the conduction current. And we will especially be interested in particles with large refractive index. So why? We will see in a minute later. Advantages of dielectric. Advantages are that there are plenty of dielectrics with low losses at optical frequency. For example, usual Windows glass. It is transparent and does not absorb light. And they're cheap and easy to get. But nothing is for free. The disadvantage is that to induce resonances in a dielectric particle, we have to fulfill the very simple resonance conditions. So, and it means that the particle could not be too small. And we need small particles for nanotechnologies. Fortunately, if we have a large refractive index, then simultaneously we can fulfill two constraints. We can get the resonance, and we could get a small geometric size of the particle. So, which practical results can follow from this? First of all, about the materials. There are plenty of cheap industrial materials which can exhibit the required properties. This is a set of commercial semiconductors. You could see the experimentally obtained curve describing the real and imaginary part of the refractive index. And we could see that, for example, for this material, at the optical frequency, this range, we have practically zero dissipation with very large refractive index. So we can easily get these materials. Which advantages could we get from this? To understand that, I have to give you a very brief reminder about theory, about Mead scattering. The key quantity for this scattering are so-called scattering amplitudes, which describe the amplitude of scattering electric and magnetic field. There are two independent modes, two expressions for this amplitude, which are called usually electric and magnetic. And then it is convenient also to introduce, because the scattering cross-section is a dimensional quantity, it is more convenient to describe the process with the help of dimensionless quantity, which is called scattering efficiency, Q, which is just the ratio of the scattering cross-section to the geometric cross-section. And then it occurs that the overall efficiency is presented as an infinite series of partial efficiencies corresponding to the dipole scattering, quadrupole scattering, and so on. And for them, we could get this very simple expression, but the dependence of the amplitude, scattering amplitude of the permittivity and the size parameter are very cumbersome, but we don't need it. What happens if we have a particle with a relatively moderate value of the refractive index? The real part of epsilon is relatively, it's about unity. So then there are a number of partial efficiencies excited when the size parameter increases. And we could see that initially we have the dipole scattering in strict accordance with the Rayleigh theory, but then we have excitation on many, many other modes with strong overlap of different lines, and we have massive lines, and we cannot excite a single resonance individually. What happens if we have large epsilon, large real part of epsilon? Then we have large polarizability, and we have large polarizability, we have large resonant amplitude. Then it means that the corresponding resonance has a very large quality factor. And if a line has a resonance, has a large quality factor, it has a narrow resonance line. And then we have weak overlap of different resonances. And it gives us an opportunity to select different resonant nodes separately and to tailor the interference. And this is a similar picture, but epsilon is increased 10 times. We could see nothing similar. The picture is similar, but the pattern is completely different. So we could see very well pronounced individual resonances and changing the size parameter. I remind you that we can do it in two ways, either to change the geometrical size of a particle, which is not convenient, but we can change the frequency of the incident light for a given particle. And then we could tailor the interference of different mode, and we could get different sketching diagrams. This is the result of this, the application of this approach to a spherical particle. And you could see that just with quite small changes of the size parameter, we can tailor and create practically any scattering diagram. And it creates the ground for, it creates the opportunity for simple and creation of simple and cheap elements for new multifunctional nano devices, optical devices. For example, if we use now I'm talking with you with the help of a computer which operates with electrical pulses. If instead of electrical pulses, we can use optical pulses propagated along optical fibers, then the CPU of such a machine will be about 1 million times larger than that we have now. But then we need completely different devices to operate with these optical pulses, and this is a way to create these devices. Okay, this is outside. What is inside? If we have large polarizability, we have large mobility of the bound charges, and then we have at higher frequency, the dielectric becomes equivalent to a conductor, and it seems that the field inside the particle should be practically zero. Is it the case? No, it is completely wrong, because we have forgotten about the polariton resonances. If the refractive index changes to infinity, then the wavelengths of the radiation inside the particle tend to zero, and then these conditions always hold. And then at given frequencies, instead of zero field, we have extremely large field. This is an example of this field, and what is for the first sight, it seems very unusual and unexpected for a particle, non-magnetic particle, which has magnetic permeability equals to unity. We have huge magnetic field. With this picture, you could see that the enhancement of the magnetic field is almost 4,000 times relative to the incident wave, not the electric field. And moreover, we can control the contrast of this field exciting different modes. So this is what I've just said, and this is some estimations about the components of the electric and magnetic fields. So what about the experiment? How to measure this? It is very difficult to put a sensor inside a nanoparticle, but we can mimic the process of scattering in the microwave region, keeping the same geometry and the same ratio of the wavelengths to the size of the scattered object. And instead of a solid particle, which is impossible to employ for measurement of the field inside it, we use a fluid, liquid. It's with a special temperature. And this is the sketch of the experimental setup. And we made some measurement. This is the calculated field. This is a measured field. You could see very well agreement, and we could achieve the enhancement of the magnetic field about 250 times relative to the incident wave. And all this occurs at the sub-wavelength scale. Okay, I am almost at the end of my talk. A few words about dynamical effects. So to get the strongest field, we have to excite high-quality resonances. If we excite the high-quality resonances, the process of transition to a steady state is very long. And then it means that if you have several resonance modes which are interfering with each other, and each of them has its own quality factor, then it means that the radiative pattern can dramatically change during the transient process. And it opens a door to absolutely new effects which do not exist at the steady state scattering. This is an example of such an effect. This is a cylinder. The calculations are made for the gallium potassium with actual optical properties, which you could see at the previous slides. And this is a rectangular pulse, which this is the orientation of the field. And the parameter of the cylinder was selected in a special way so that at the steady state, the scattering is extremely weak. But it's at the steady state here. Here you have huge spikes related to the transient process, which, as I stress, do not exist in the steady state. And they are very short. So we can, a very simple way to generate very short intensive pulses just illuminated by a rectangle long pulse, a particle by a rectangle long pulse. This is a certain model, which analytical model, which we developed to describe this effect, and you could see a very well agreement between the numerical calculations. And this is the result of the numerical solution of the complete set of Maxwell equations, and this is our model. Moreover, this dynamics corresponds to the changes of the scattering diagrams. You could see the scattering diagrams for these processes, and the blue line is average over a period of oscillation, and the red line is the instant intensity. So now we are already here, and then we will jump to the end of the pulse, and you could see this spike. So then there are two scattering diagrams, three scattering diagrams in the characteristic times, and you could see completely different directionality of the scattering. And all this is limited, is bounded by a very narrow solid angle, and this is actually a very simple nanoradar, a particle with a nano size which could emit in a certain direction a powerful light radiation. Okay, so I'm at the end of my talk. So conclusions. At resonant light scattering by subwavelength plasmonic particles with a small dissipation rate, the non-dissipative radiative dampers play a dominant role. In this case, the scattering is anomalous and has very little in common with the conventional Rayleigh one described in the textbooks. At the anomalous scattering, there is a funnel in the Poynting vector pattern. The funnel collects the incident radiation from a large inlet downstream and conveys it to the immediate proximity of the scattering particle. The subwavelength near-field pattern to the Poynting vector exhibits various types of singular points whose type and position are very sensitive to the frequency of the incident wave. Resonant light scattering by subwavelength high-index dielectric particles with a low dissipation rate may be employed to create tunable scattering diagrams. This effect may be a basis for designing and fabricating a new type of simple and cheap multifunctional optical nanodevices. This scattering may be accompanied by a huge electromagnetic field concentration within the particle, and in its turn, it create ground for numerous nonlinear effects, which I do not discuss in my talk. Notably, the enhancement of the magnetic field in non-magnetic particle is about square root of epsilon times larger than that for the electric field. The field pattern within the particle has a tunable contrast, and the tuning is achieved by the varying the frequency of the incident wave. The main publications are here. And this is the funding of this research. And that's all. Thank you very much for your kind attention. I am ready to answer your question.